Hello, my name is Saurav Bose, and welcome to the presentation on detecting predictive signatures of asthma in pediatric breath samples using machine learning. This is a cross-institutional study with researchers from the Children's Hospital of Philadelphia, Washington University School of Medicine St. Louis, and AI Cure New York. A quick disclaimer before we proceed. The study was approved by the Institutional Review Board at the Washington University School of Medicine, and informed consent was obtained from a parent or legal guardian prior to inclusion in the study. So why is this study important? Well, asthma is a common allergic disorder that affects at least 300 million people and accounts for up to 1 in 250 deaths worldwide. However, the current state of the art of diagnostic testing for asthma are either invasive or require patient compliance. This makes them difficult to use in children, and there is a real need for a better alternative. Recently, there has been some traction in using computational tools to mine breathomics data to distinguish between asthma subtypes. In this study, we collected breath samples for children with and without asthma and built on prior research to develop a novel end-to-end computational pipeline to achieve two goals. One, distinguish between asthmatics and non-asthmatics, and two, identify biomarkers that correlate with asthma. The study cohort included 43 children between ages 6 and 12 years. Out of the 43, 14 were asthmatics, which was about 33% of the population, and 29 were non-asthmatics, which is about 67% of the population. Our data analysis pipeline consists of 6 components, and that's presented here in chronological order. First, raw data was extracted from the breath samples using the GCMS system. Ion peak detection was then used to create a structured dataset of ion intensities. Dimensionality reduction and filter-based feature selection were used to transform the high-dimensional feature space into a low-dimensional dataset. Binary classification algorithms like the XGBoost and logistic regression were then used to classify each of these data points into asthmatics and non-asthmatics. The most relevant features used in this classification were used to identify compounds that can serve as biomarkers for asthma in the future. Now let us look at each of these components in more detail. This is what a GCMS, or gas chromatography mass spectrometry system, looks like. In the first step of the pipeline, breath samples are passed through the setup where they are broken down into constituent fragments, which are generally charged, and so we call them constituent ions. And a computer plots the chromatograms of the fragments. Chromatograms are plots of the abundance versus retention time. Abundance is simply the concentration of the compound in the sample, and retention time is the time it took for the compound to pass through the GCMS system and be detected by the computer. This time depends on two quantities, the mass and the charge of the compound, and together they are represented by the m/z, or mass to charge ratio. These chromatograms are then processed to detect the peaks and generate a list of compounds present in the breath sample. The data obtained is as seen in the figure here. The rows are unique breath samples. As an example in the image, the first 3 rows are breath samples of healthy patients, and the last 3 rows are those of asthmatics. The columns represent the various compounds identified, with each compound's name represented by its mass to charge ratio and retention time, as seen in the column headers. The actual values in each cell of the matrix is the abundance of a compound in a given sample. This dataset resulted in 2,734 features. With only 43 samples to work with, we were dealing with a very wide dataset, which we know is not ideal for machine learning. This presented a need for intelligent feature selection. We implemented several of these feature selection methods to reduce the dimensionality and retain the most relevant information in the dataset, as you can see in the table here. CDR stands for correlation-based dimensionality reduction. ANOVA is a univariate statistical test which is used to select features that correlate with the outcome, and ReliefF and MultiServe belong to a class of algorithms that select the most relevant features based on a distance metric. Each of these feature selection methods resulted in a subset of the original dataset, which was then used to train an XGBoost model, which is a tree-based machine learning algorithm. The hyperparameters of XGBoost were tuned using Bayesian search and leave-one-out cross-validation. We also repeated our experiments with logistic regression, which is a linear model. In our experiments, we found that CDR followed by ANOVA followed by ReliefF performed the best, and that the XGBoost model consistently outperformed logistic regression. Here you can see the ROC curves of the XGBoost model in combination with the various feature selection routines. The ROC curve plots the true positive rate on the y-axis against the false positive rate on the x-axis for the various decision thresholds between 0 and 1. The diagonal line represents the area under the ROC curve of 0.5, which corresponds to a random classifier. As you can see, the XGBoost model, in combination with any of the feature selection routines, significantly outperforms a random classifier. Now let's take a deeper look at the feature selection process. As you might recall from the previous slides, the most optimal feature selection routine was the correlation-based dimensionality reduction, which we call CDR, followed by ANOVA, followed by ReliefF. In CDR, pairwise Pearson correlation is computed, and for each pair that has a correlation of greater than 0.95, only one feature out of the two is retained. Next, the ANOVA test computes the F statistic between each of the features and the binary outcome. It checks whether there is equal variance between the two groups of binary outcome, that is, asthmatics and non-asthmatics, with respect to the continuous features. Equal variance between groups would mean that the feature has no impact on the outcome and so should not be considered in the model development. We set this feature selection process as a hypothesis test that is performed for each feature one at a time, and the F statistic is used as the statistic of choice. The null hypothesis is that the variance is equal, and so we only retain features for which p-value is less than 0.05. That is, we retain features when we can reject the null hypothesis. Finally, let's see how the relief algorithm works. Consider two breath samples, which are the rows in our dataset, one coming from a healthy patient and the other from an asthmatic. In reality, each row is represented by a sequence of numbers, but for now, let's abstract away and consider them to be a sequence of letters, as shown here, to develop our intuition. The algorithm iterates over each of the rows in the dataset. Let's say the first row encountered is the sample of a healthy patient. We call this the target. The algorithm will now find a row that is most similar to the target but has a different class. This is called the nearest miss. As we go through the sequence, we see that most letters are the same between the two rows, but some elements are different. And the intuition here is that these elements that are different are the reason why the two samples have a different class. And so the algorithm upweights or adds a weight to this feature. Similarly, it also finds the row that is the most similar to the target and has the same class. We call this the nearest hit. The intuition here is that the elements that are different between these two samples are redundant, because even though their values are different, the class remains the same. And so we downweight the feature. In practice, however, we are dealing with a sequence of numbers and not letters, and so we don't look at equality in making these decisions, but the magnitude of difference between the feature values. Now the algorithm goes through all of the rows in the dataset, finding the nearest hits and nearest misses, and upweighting and downweighting the features. And at the end of the process, we have some final score for each of the features. We then retain only those features that have a positive score, because those features have been upweighted more than downweighted, or in other words, deemed important more often than not. Now, this entire feature selection procedure is embedded inside a leave-one-out cross-validation procedure. So feature selection is performed independently 43 times for the 43 train validation folds corresponding to the 43 samples in our dataset. The features that were chosen in at least half of the validation polls were considered to be important. We found 17 features to be important. We then looked at the mass to charge ratio and the retention time of each of these 17 features, examined the corresponding chromatograms, and identified constituting compounds using the NIST-17 library. We were able to identify 5 compounds that discriminate between asthmatic and non-asthmatic breath samples with good predictive performance. Of these, toluene and pentanoic acid have been previously observed to be associated with asthma. 3-carine was observed in a previous study to be discriminatory in the breath samples of patients with and without a risk of developing VAP, or ventilator-associated pneumonia. Cyclohexylmethane has not previously been cited in the context of asthma, but is known to be present in breath samples. L-alanine 3-sulfur has never been reported to be present in breath before. Although the biomarkers identified in this study are preliminary, they have the potential for future use in portable devices such as electronic noses, which can be a viable replacement for the current state-of-the-art in pediatric asthma diagnosis. However, future research is warranted to understand the origin of the discriminatory compounds that we have identified and study their relation to the pathology. Thank you for your time, and here is my email in case there are any questions.